We're asked to rank the relative stability of some resonance structures, so let's first draw the structures. Alright, so we've counted up the valence electrons. We see we have 12 electron pairs. Carbon's listed first. We'll put that in the middle. And we'll have the chlorines on either side and oxygen here. Alright, we'll discriminate between the chlorines this way. Alright, so we have 12 electron pairs. Let's complete the octet of the outside atoms. And we see that we've used up all 12 of our electron pairs completing these octet. But the central carbon atom only has 6 valence electrons. Remember, each of these bonding pairs counts towards both bonding partners. So the carbon here is electron deficient by 1 E pair. So we have to have one of these lone pairs on one of these outside atoms convert to a bonding pair so that carbon can be a full octet. Alright, so here are the structures for the 3 resonance structures. We can put the double bond in place, let's say here with the oxygen, here with chlorine A, and here with chlorine B. And we complete the octet of all these outside atoms and see that we've used all 24 of our valence electrons, all 12 of our E pairs. Alright, now we need to determine the formal charge of each atom in each of these resonance structures. Alright, so we've done this and we've done our sanity check to make sure that the sum of the formal charges is equal to our net charge, which in a compound is going to be 0. Now let's rank these. We see first off that structure 1 is going to be the most preferred, most stable, because all of the formal charges are 0. Now we look at the structures 2 and 3, and in each of them we see that the -1 charge is associated with the oxygen. So each of these is equally preferred, but not as good as structure 1.